Here we have in question A, it says define the energy density of a fuel. In a definition, you really got to note clearly what that definition is. So the energy density of the fuel is the energy released from that fuel per unit mass. In our list of definitions, we have it here. This is here, the energy density of the fuel, the ratio of the energy released from the fuel to the mass of the fuel consumed. So it's the energy released per unit mass of the fuel. Going on to question B, we have the following information. It says a room heater burns liquid fuel and the following data are available. We're given the density of the liquid fuel, the energy produced by 1 meter cubed of liquid fuel, the rate at which the fuel is consumed, 0.13 grams per second, and the latent heat of vaporization, 290 kilojoules per kilogram. Then it says use the data to calculate the power output of the room heater, ignoring the power required to convert the liquid fuel into a gas. So in doing this, we need to look at these values over here. We have the density of the liquid fuel, the energy produced, and also the rate at which the fuel is consumed. We don't need to worry about this because it says we can ignore the power required to convert the liquid fuel into gas. So we don't need to worry about that for a moment. So in looking at this, we need to remember that an important formula is that our density, which is often given by this symbol, a rho, is equal to our mass over our volume. So in looking at this, I'm interested in the volume per second. The volume per second. So I'm going to have my volume is equal to my my mass divided by my density. And here I am given a rate, I'm given a 0.13 grams per centimeter, so grams per second. So I'm given a mass per second. So if I've got a kilogram here per second, and I divide it by the density, which is your mass over your volume, your kilogram per meter cubed, can you see that my kilogram is going to cancel out? The meter per second is going to go to the top, and I'm going to get a meter cubed per second. I'm going to get a volume per second, which is what I want, because I'm looking at the power, which is an energy per second, and here I've got the energy that comes from 1 meter cubed. So if I multiply that times my meter cubed per second, I will get my answer. So here we're going to get our volume per second. I'm going to put my V per second here, is going to be 0.13, but this is grams. So remember, grams to kilograms times 10 to the negative 3. That's going to be kilograms per second, and I'm going to divide that by my density, which is 8 times 10 to the 2, so it's going to be 800 kilograms per meter cubed. Now I'm just going to go down into this part over here where we can continue working. So my volume per second is going to be this. Now notice my kilograms cancel out, and I'm going to get a meters cubed seconds to the negative 1 coming in, because that's going to go to the top. And when I calculate that, I get about 1.63 times 10 to the negative 7 meters cubed per second. So that's the number of meters cubed per second that is being used. And here I've got my energy per meter cubed. So my energy per second is, I'm going to multiply this value times this, because this is per meter cubed, I get this amount of energy. So I take 1.63 times 10 to the negative 7 meters cubed per second, meters cubed per second, and I multiply it by that 2.7 times 10 to the 10 joules, and this is a per meter cubed, so that's going to cancel with that, and I'm going to get a joule per second, which is power, and I get out of that about 4,300 4,387.5, which is about 4.4 kilowatt. I do to two significant figures because I've been given all my data in two significant figures. Okay, so that is that part. Now let's go into this next part. It says show why in your calculation in B1 the power required to convert the liquid fuel into gas at its boiling point can be ignored. Well, here we know that we need 290 kilojoules per kilogram to convert 1 kilogram into a gas, and I'm using 0.13 grams per second. So 0.13 times 10 to the negative 3 kilograms per second are being converted, and for each of that I need this many joules. So it's times 290 times 10 to the 3, because it's kilojoules there, kilojoules per kilogram. So I see here my kilogram cancel out, and here I've got a joules per second, which is a watt. And when I multiply that out, I get a value of about 38 watts. Now, 38 watts in comparison to over here, 4,400 watts is less than 1%. So it's less than 1%, therefore not significant. Not significant. Now, as you can see here, by using our units, we can see where we are going. So you can always check your units to see whether the unit that you get out, in this case our joules per second, is correct, as a check and also as a guide to how you can solve the problem. For C, it says state in terms of molecular structure and their motion two differences between a liquid and a gas. So we're looking at molecular structure and their motion. So in molecular structure, we see that in a liquid, we have that there's structure in a liquid. We have structure. You have it that there is some sort of order. There is some sort of order where a gas is random. A gas is random, and there are no forces in between. No forces, intermolecular forces. Molecular forces in between. And as far as their motion is concerned, we have in a gas, we have long distance motion, we have translation, and in a liquid we have more rotational and vibrational motion.